एस्केप करके कराना क्या कर रहे हो कराना Right, let's start. So there appears to be a lot of jargon in this paper, in the abstract itself. So let's first break down the jargon. I'll read the abstract line by line, and then I'll explain the key terms used here. So, right, so it refers to an advanced controllable image animation method. So basically, control image animation refers to the process of animating a static image into a video with the ability to control certain aspects of the motion. So in the context of this paper, in image animation, controllable means that you can specify how parts of the image should move rather than relying on the system to decide everything. Right. So moving on, let's talk about controllable signals. So controllable signals are just extra pieces of information that help guide the video generation process. They can include human landmark references, manual trajectories, or other videos also. And multiple signals can be combined to create complex animations. So, let's talk about human landmarks reference. Human landmarks are specific points on the human body, like joints or facial features, used as reference points for motion. So, for example, in motion estimation problem, where given an image of a human, the model will tell which pose the human is in. So, for example, if you send an image of yourself sitting on a bench, then the model will tell that you're sitting, that you're in the sitting pose. And in the context of this paper, MOFA-Video, which is the topic of this paper, can create animations that follow realistic human movements based on these reference points. So this model won't create some absurd human motion that is not humanly possible. Let's talk about manual trajectories. Right, manual trajectories. So these are just user-defined pathways or movements that parts of the image should follow. And in the context of this paper, it allows users to manually specify how they want certain elements of the image to move, and thus giving more precise control over the animation. Right. So one more jargon is motion domain. So motion domain refers to a specific category or type of movement that an animation system is designed to handle. And in the context of this paper, say, for example, in the context of an image and video animation, a motion domain could be human motion, animal motion, object motion, etc. Previous methods that work on a specific motion domain are tailored to handle only one type of movement, meaning that they are limited in the versatility and cannot easily adapt to different types of inputs. So, for example, a system designed to specifically designed specifically for human facial animation might not be able to animate other kinds of objects effectively. Now let's talk about weak control abilities. Weak control abilities. So basically, they refer to the limited capability of a system to allow users to influence or direct the outcome of the animation process. So for example, in previous animation methods, weak control abilities meant that users had minimal options to specify how the image should move. And this could result in animations that do not accurately reflect the user's intentions or lack the precision needed for certain applications. So like users might only be able to provide very basic inputs, and the system would have limited responsiveness to these inputs. Now let's talk about diffusion prior. So diffusion prior is a statistical model or technique used in the generation of data, such as images or video frames, that relies in a process of gradually transforming noise into the desired output. Basically, how a diffusion model works. And in the context of this paper, in image and video generation, diffusion models are used to iteratively refine an image from a noisy starting point, guided by a learned process, guided by learned patterns in the data. But relying solely on a diffusion prior can lead to less control over specific aspects of the generated motion. The term just a second. The screen is not working. It just turned off. Hmm? Oh. Right. Yeah. So the term weak control abilities with diffusion prior implies that. So this term weak control abilities with diffusion prior. So this just means that while diffusion models are good at generating plausible images or videos, they might not offer fine-grained control over the specific movements or animations desired by the user. And in the in the combined context of this whole sentence, it means that so this sentence highlights certain so this sentence means that so motion domain means in the sentence that previous methods were typically restricted to handling only one type of motion, making them inflexible when faced with different kinds of input data or requirements. So let's talk about the methods, the jargon that is used by the topic of this paper, which is MOFA adapters. So this is domain-aware motion field adapters. So being domain-aware means having the capability to recognize and adapt to specific contexts or domains of information. And in the context of MOFA-Video, domain-aware refers to the system's ability to understand and adapt to different types of motion domains, such as human motion, object trajectories, or any specific type of movement context. And this ensures that the motion generation is tailored and accurate for the specific type of input provided. For example, human landmarks versus manual trajectories. Motion field here means, so motion field is a representation of the motion of points in a space, often a 2D or 3D scene over time. And it typically shows how each point in the image moves from one frame to the next. Let's talk about adapters. So adapters are just components or modules designed to act as an interface between different types of inputs and the main system, translating and transforming those inputs into a usable format for further processing. And the combined context of domain-aware motion field adapters, so each part works together to create a robust system for the controlled video generation process. Right. So MOFA adapters uses temporal consistency of the video and generates dense motion flow from sparse controlled conditions first. So this means that so temporal consistency here means that the smooth and coherent motion over time in the generated video, and using sparse controlled conditions means that the input has very limited or minimal information about the desired motion. So for example, just a few landmarks or just a very basic trajectory. And using these sparse inputs, MOFA adapters focuses on the temporal consistency and generates a dense motion flow. Dense motion flow means, so it's a detailed representation of motion for every pixel in the image. So first it does, generates a dense motion flow from these sparse inputs, and then focuses on the multi-scale features. So multi-scale features are basically inputs that have very detailed or nuanced information at different levels or like of detail. For example, low-level features might capture fine details like edges and textures, while high-level features might capture broader patterns and shapes. Right. So, MOFA adapters basically, I'll again repeat the whole thing so that it is clear. So MOFA adapter for like takes the sparse controlled conditions, that is sparse inputs with limited information, and focuses on the temporal motion consistency, that is the time related aspects of the input, and then generates a dense motion flow from these sparse inputs. So this is the first step. And the second step focuses on multi-scale features of the given image. As I told you about multi-scale features, so it then uses those multi-scale features and uses that as an example for stable video generation, stable video diffusion generation. So video diffusion generation, yeah. So generate that. No, so dense motion flow. So basically, it's a detailed representation for every pixel in the image. So like you're moving from one frame to the next, and like you have a video, and say for example there are 10 frames in the whole video, right? So dense flow just means that so when you're moving from frame one to the next, the dense motion flow will contain information about like how every pixel should transform, to so as to. Oh, about this, like how. Okay. Yeah, so it's still right. So right. So let's talk about the video diffusion generation process. So this is a process of creating video frames using a diffusion model. And as I told you, like diffusion model like iteratively refines the frames from an initial noisy state to a clear and stable state based on the motion flow and features. So MOFA-Video naively trains two motion adapters. And like one is used for manual trajectories and the other is used for the human landmarks. Right. We'll talk about the methods in like in the coming section. So I'll just talk about the whole summary of the abstract. MOFA-Video is a sophisticated method for animating images into videos with high user-defined control, and it uses domain-aware motion field adapters to handle various types of control signals like human landmarks and manual trajectories. And these adapters ensure the temporal consistency, meaning consistency over time, and detailed motion flow. This results in smooth and realistic animations. And by training these adapters individually for different controls, MOFA-Video allows for precise and versatile video generation, overcoming the limitations of previous methods. So let's talk about, let's move on to the introduction part. So I'll just quickly go over what the introduction covers. So it basically like there are two methods of animating images into videos. The first one is like talks about traditional computer vision algorithms, but the limitations here are that they focus only on a limited category of animated objects. For example, fluids or human hair, basically the objects that are easy to animate. And then next it talks about image to video diffusion models. So yeah. So do you have any questions about the abstract? All right. let's talk about the previous methods. So mainly there are two things that are discussed here: controllable image animation and image to video diffusion models, which was also discussed in the introduction, but I'll cover it here. So controllable image animation, so in controllable image animation, I mean, there are different ways to control the input to the video generation pipeline. For example, text control, class control. So for example, you can use text to control to guide the video generation process, or maybe classes. Like for example, when you're dealing with an MNIST, like the MNIST data set, the MNIST rigid data set. So there are 10 classes. So this is what class means here in the class control. Like there are different ways to control the input to video generation pipeline, and you have and the different ways you have text control and class control. And recent works only control a few objects like fluids and human hair because they're easy to animate. And MOFA-Video uses different and possibly more domains and uses a pre-trained video diffusion model. So what is a pre-trained video diffusion model? So this model has been pre-trained on a large data set of videos to learn the probabilistic patterns of video generation, and it uses diffusion processes to gradually transform noise into coherent video sequences, guided by the learned patterns. So in the image to video diffusion models, we have two examples. Like I'll cover two examples: drag nova and motion control. So in the drag nova architecture, we basically drag the image, and from that motion, from the dragging motion, drag nova can generate a video. But the problem here is that there is not a proper correlation between the images across different frames. So like the video appears a bit jittery and erratic. Sure. So this is the drag nova architecture. Right. So I guess you can use the input image and maybe drag this around, and then this architecture will generate the motion of the like the motion from the dragging, and maybe I guess so. Yeah. Right. So this was the drag nova architecture. Next, we'll talk about uh, motion control. Motion control architecture. So motion control architecture uses a text to video model. Basically, you give text and it will generate video for you. But it is hard for the video generation process because there is no world coordinate system. World coordinate system just basically means that I'll just use a very simple analogy here. Say, for example, you are moving and there is someone on the moon watching you. So basically, it is watching you moving and how the Earth is also moving. So this is like world coordinate system. Yeah, so these are the two architectures in the related works. This is the motion control architecture. And as I talked about the world coordinate system, so I guess this is like how the camera is moving in the camera pose. These are different camera poses. And there are like two coordinate systems. One is the camera coordinate system and one is the object coordinate system. But I won't go into the details here. Yeah, so that was about the related works. Yeah. Any questions so far? Okay, now on to the methods of MOFA video.
We can talk a bit about methods.
Yeah, sure.
Okay. So, so I guess like the problem from what I saw they were trying to do is I also like don't think this is video generation because uh, yeah, I think like this is animation. So I also think like this is animation and not really video generation. So I yeah, I also like don't buy the video generation like the title of video generation because you're only like you have an image and then you're trying to move certain things in the image to create frames. So that's not really video, right?
They did say image animation though in the title.
Paper's very dense. I just skipped through it.
Yeah.
Oh, chart.
Oh, I see. I guess like the other thing is the paper is also very new and so I was reading this actually earlier this morning and I found a bunch of mistakes. And these are like small, even like smaller things like grammar mistakes and also like some larger like writing stuff. So I guess like this is a bit new, but the but it got really like famous in the past 1 week. It's like week and half old paper, I think, and it got really famous in like past 1 week. So yeah, maybe like we can start by talking about methods. So yeah, so I guess like they start by they have an overview figure here. So maybe let's see this. So I think like this is the two things they are trying to do. One is, and these are then like different yeah, these are like different trained models. So it's best to like think of them separately. There's a lot of like similarity between the two. So maybe we can we can like talk about that in the second stage, but the training is separate. So for all real purposes, they are separate models. So one is they have like this thing where you give a portrait. So this always has to be a portrait of a person, and then you give like these points. So these would be things uh, like how does the face look at at different points. So just like a landmark of the object. So yeah, they have like these face frames at different times, and this is like given by the user. So the user says exactly how the face should move, and nothing else in the image should essentially move. Like the background should stay the same. So that's like one of the problems they are tackling. And the other problem is you keep the background and everything same, but you don't have maybe you could have people where you have like general images and then you do stuff like so if you have an image over here with the rocket like them, then what you do to create this kind of stuff is that the user comes in and the user says that oh, the rocket should move this way, so he'll like probably drag this or like the way they do it, I also tried running their code, is that you can actually like highlight this area and then you can mark a vector. So the blue would be like the user marked vector, and that vector would say, oh, this object should move this way. So 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 that is like the second problem they are tackling. Um, and yeah, these are like separate problems. And the other idea they had was like, so this is like how the inputs are, what the inputs are, and then of course you want like videos, but what they are trying to do is also that from what I noticed, um, it's individual frames of a video. It's not um, so if there was a better way to put it, each frame of it's like very small videos and they have very little motion in them. So it's not like idle motion. So I guess like if you see yeah, all of these 4D. Sorry, why do they have to? Oh, no, they are only able to do short videos, apparently.
Well,
Oh, yeah. So one of the things with that is that so you can only extrapolate the motion up until certain point. So this motion extrapolation is a different thing altogether, and then it's being passed to like the video generator. So what happens is you have a lot of guidance vectors over here that need to be followed exactly. And as soon as you like start increasing the context length for all of these guidance, things start to fail. And the larger the context length, the harder it is to like follow it. So if you go to very large videos, you need to have this for every single frame, and then it doesn't like follow it any longer. So uh, yeah, maybe like we can. So they also like.
better.
I mean, for very large videos, I would assume the best way to do it to answer the question. Like, I don't know for sure, but and I haven't explored this, but probably the best way I think would be instead of doing this, you make the model fully auto regressive on a video window. So if you have like a video, then then you make it auto regressive, of course, fully auto regressive, and then each generation only accurately depends on this window of uh, the video. So like all the previous thing from the context gets wiped out entirely. This generation only depends on like a window of the previous generation. But from what I've seen, like this is also not without challenges. Uh, People have tried to do that. Yeah, exactly. But this would theoretically allow you to generate infinite videos,
Sure.
I guess. Uh, So, yeah, maybe like let's go over methods. I guess like they also talk about control net, which is nice because this does remind one of control net quite a lot. Uh, so yeah, that's nice. So yeah, they start by talking about generative motion field adapter. So I guess like this is an overview, and then they talk about how to train the model, and then they talk about inferencing the model. So I guess like for this part, we can mainly take a look at this figure, which seems to be the main figure for like how the entire model is kind of built. So I guess from here you okay so the user only, so in terms of portrait you have like all of these things that the user gives you, so that's somewhat easier, but you still need to do some work to get like exactly how the motion should look like, because this is only very sparse, so you still have to do some work. But over here you have to do a lot of work because the user only like drags certain things or highlights it. So maybe we can like see how they do that first. Yeah. So it seems like yeah, so this seems to be the main figure. And they show the example for like this sparse motion hint. Um, but this should be but this seems to be like the case for like the parts where the user drags it as well, like the other model as well, where you don't have like facial features of sorts. So yeah, maybe like let's take a look at this image. So first they have like this sparse to dense motion generation network, and they say that they take a lot of this a lot of like inspiration for sparse to dense through CMP. Uh, so that's interesting. And they also so, oh, so um, and they also say that uh, then you do like some kind of warping on these features. So I guess like let's come to that. But firstly, do this sparse to dense generation. And so the way they do it, and I guess like the conditional motion propagation had a really nice figure for what they do, because they pretty much do a similar thing, like the what they call watershed features for motion estimation. So they try to do something very similar, to make like dense motion maps. So and I remember like I don't know if you remember this super popular paper which came out in like 2019, and they did like this motion stuff really well. So yeah, they had like this figure, which these people use as well. So what they do is you take an image, you ignore the red dots for now, but you take an image, estimate an optical flow map. But then like the optical flow map is like all of these vectors and like super high resolution. Like it's like for every pixel you have like a vector. So then what you do is just do non-maximum suppression on this. So I just do like a rough approximation of like canny edge detection and get like these flow edges. And then on these flow edges, what you do is take like uh, once you get like flow edges, then you sorry, I should have like reset this in a proper way. Once you get like the flow edges, do like some kind of edge detection, then you do non-maximum suppression. So you get like all of these regions where you have like very thin edges, and those are the only things that you need to move, or approximately need to move to get to like the next frame. A big problem with this is uh, is like things. So big problem with this is like what people often do is approximate what would happen if you do the watershed with a very large kernel size. And if you approximate that, you would happen to get like very idle motion. So qualitatively, your results should seem similar to like all of these dynamic 4D models, which like do very little motion, and it's just like idle motion for the most part. So, so I guess like you also have to be very sure to choose a good kernel size that fits in memory. Uh, and Oh, and like these people for the flow to flow edge, they don't do anything complex at all. They just use a Sobel filter on the entire image. That's all, and then do non-maximum suppression. So
Top two.
yeah, yeah, yeah. So this is how they sample guidance from like the optical flow, and get like all of these dense guidance vectors. Uh, but like there is also another problem, uh, which is something that Aryaman talked about briefly. And I think this is still a big problem with this paper, but they only kind of partially solve it, like MOFA-Video as well, which is there is always ego motion, and that isn't captured very well in optical flow. Uh, because like all of these optical flow estimation methods, usually they don't take into account ego motion, but we expect like all the video generation models to have ego motion because you see Sora and the camera is moving as well. So you want ego motion, but the optical flow doesn't take it into account. So an easy way to like approximate this is by drawing like these red colored things. Just like make a grid, and then just like care about what happens in a single grid. So so then you can get around some of these effects of wrong optical flows due to ego motion. But this isn't like a full-fledged. If you really want to do it, I guess then you need like bird's eye view and all of these proper world coordinate models. That they don't do, but kind of gets around ego motion for optical flows. But so I also saw their results. The results don't have a lot of ego motion, and I can probably like show that in like a while. But I would assume that this is the case because you can't do it so well with like these kind of methods. But anyway, so you did like the optical flow estimation, you did this sparse to dense motion. So now you have like all of these dense motion vectors. Then like what you want to do. So another thing that's really interesting about this paper is that they define their problem to be, well, it's image animation, but the first frame of the animated thing should be exactly the same image. It can't be, so you can't, for example, like the most popular way of doing image animation by far is you take stable video diffusion, uh, then you run your image through a clip model, get like the clip embeddings, and then pass that as a conditioning vector for to the stable video diffusion. So so then you get approximately similar things to the image, and and then you can still create a video through stable video diffusion. You don't need to do like a lot of train. Well, you need to do some adaptation, but that's all. Um, so that's, I guess, like a very easy way of doing this. But that doesn't work when you kind of want like this identity preserving stuff where the first frame should stay the same as like the frame you give it, because the clip embeddings will of course like not retain the information. So yeah, so they want like the first frame to stay the same, and like what they do for this is um so so this is where you have like the stable video diffusion. So let's like leave this for a moment, because this is like a pre-trained stable video diffusion model, nothing new over here. um so then what you do is the main part of this is like training this fusion encoders, and what these fusion encoders do, and this is where like most of the training goes, most of the training is required, is that if you actually go to the other figure image they have, so when you want to do this, you already did the sparse to dense, and then when you want to like do this warping on based on the first frame as well as like the dense video vectors, to give it to stable diffusion you need to train like this small adapter network, because yeah, this is just like a pre-trained stable video diffusion, so you need to train like some joint embeddings that can like that those are like joint embeddings for the decoder part of stable video diffusion, and for like whatever this warping stuff produces. So this is where you like, oh sorry, what's the question? I forgot, I didn't get. Oh, oh, I see. Oh, yes. So the idea with stable video diffusion is actually really straightforward. Uh, what you do, they have a lovely figure. But like it's not even one of those image to video models. It's even more straightforward. Okay, never mind. But so what they do is you have your standard unit, and uh, people after stable video diffusion figured that you can use the image weights to like initialize the unit, but never mind. So exactly what stable video diffusion does is you have your unit, which has like uh, and then you add an extra spatial channel, uh, do memory units for just make it like a recurrent network of sorts. Um, And then you have the extra spatial channel, so you get all of the video frames that the diffusion looks. Exactly. Exactly. It's kind of just extending a channel. And the reason they get like really good, I guess, like outputs. Oh yeah, this is actually the thing I was looking for. Uh, yeah, this is like from their paper, and they essentially just do this. They have new temporal layers, and conv becomes const 3D. That's all. Uh, but like they spent a lot of time doing data stuff in stable video diffusion. So they have a really big data set that's synthetically generated, but then it's like there's like one branch that goes through a blip model, the bootstrap image language image priors model, and then there's another one that goes through other kind of there was another model that they use, another kind of image to text model. Then they use both of those embeddings, train an LLM to generate, to score both of those embeddings, and then generate a text prompt for it. So they do like a lot of stuff on the data side of stuff. And like most of their paper is actually, most of the SVD paper is actually about like, how do you do like all of this data stuff really well? And then they do like, of course, pre-training, fine-tuning, very and then they just like stable diffusion, like if you see stable diffusion 2.1 or deep fluid if, and the both of those models, the way you best train them is you take small images, then you take large images, then you take even larger images, and then when you are training, you across different gradient updates, you change what kind of images you'll use. So like the first few gradient updates, I don't remember the exact number, but like the first few gradient updates will only use this small images. Then you use larger images and so on. They do the same with videos as well. Yeah.
Can you use points regularly?
Oh, you can, and there are a lot of methods that do that. So the most naive way of doing it, I guess, is you take a conv 2D. Okay. Yeah, you take like a conv. Let's say for the moment this is a con 2D. Let's not talk about attention layers. But anyways, you take like a con 2D. This has probably uh, you add one more spatial channel to it, make it a. So I don't know why my pen is not working, but you essentially make this a con 3D. And what you do is you take all the weights, copy those to the additional channel. So if you have like all the weights, you copy this into the additional channel, and then you do like in code, you do a simple reduce function for all of it, but ideally just like sum and average. And that's a really nice starting point for video diffusion models. Uh, but like I guess like this is the most naive way of doing this, and people used to do this like for activity recognition on kinetics and that kind of stuff in like really early times. Uh, but there are also better ways of doing it. So one of the most popular kinds of approaches is um, you take a pre-trained text to image model. You don't do any training, but then you take previous frames, find some way to put them as in as conditioning vectors, and then you just like essentially have a zero shot way of generating videos from text to image models. So you can do that as well. Then you have like one shot methods, like few shot methods as well, to do text to video from text to image. So I guess like those are the three most popular classes, at least that I've seen. Maybe I missed something, but yeah, I guess like those are really popular ways of doing text to video. SVD is, I guess, like in a nice, interesting, easy way or straightforward way of doing it, I guess. So so I guess like one of the main things was like after this warping network, you need like a fusion network here. So this fusion network is what they are actually. So this is so they missed drawing it. Probably it was intentional or expected, and maybe I can't read it well. But you have a fusion network here, and that fusion network is like all of this. And this is the thing that goes to the SVD decoder part. And what this fusion network essentially does is takes the results from warping. And so warping is conditioned on the dense motion, and it has the inputs of the first frame. So yeah, so that is what you have for warping. And then you take the warping and then you train this fusion network, which is just like a way of passing it into SVD because you need like joint embeddings, right? So this just like takes care of passing it into SVD. And essentially like that's how both of the models like this thing where you do portraits and the other one where you do standard objects, both are built. So that's how they like essentially build it. And yeah, they also say it's like really reminds you of control net because they do something very, very similar, of course, for 2D. And there's also control net motion, which does something really similar. Um, yeah, this does remind you of control net. So yeah, then they like talk about training this model. So yeah, training this model is actually uh, is now somewhat straightforward. You have like a different model that they don't train that extracts all the optical flow maps. And then so one now that you get the optical flow maps, you use this watershed sampling from which is like the which is like the figure I was showing over here. So then you use the exact same thing to get like sparse masks. Then you have your S2D network to get the dense marks, and uh, then you can just like use that fusion network and warping network. So you can train the entire thing, but you don't have to train stable video diffusion. You only have to train the adapters for this. So and this is like they talk about like doing the human key point thing. So this is like not natural motion fields. Yeah, different from natural motion fields. And uh, but the training for this is pretty much similar. They train both individually and have like separate sections for it as well because they are separate models. But the training is pretty much similar because you essentially have the same things. It's just that you already have the sparse motion vectors. You don't need to do all that CMP stuff for sparse motion vectors because the user gives it to you. So then they have a few results, but probably it's like better to see these results from the website. And oh yeah, the training is like very standard. This is like the standard loss. Uh, this part is the adapter that is conditional on the initial frame. Uh, uh, yeah, and you just like train these adapter weights. So, but essentially like use the same loss. And so I guess like then they have a few results and a bit of evaluation of some sort. This is a user preference evaluation, so I guess we can skip through that. And then they also have like some metrics for drag NUA versus theirs, and then oh well, this is fully user study, so never mind. Uh, but for like standard motion, they have like quantitative as well. So it seems to do better than drag NUA, but yeah, I guess like there's not a lot of things you can make out from metrics, especially in this because yeah, exactly. Yeah. So I guess like we can skip through all the evaluation metrics. But they do like the standard evaluation. Like they do like path similarity. They compare the clip embeddings. So and on those it seems to work well. So I guess they do use all the standard evaluation methods that one should use. And then they had like a few interesting results on their website. So so this is like the general object thing where you have like all of you highlight something and then you have like all of these vectors that the user gives you. And this actually looks good. There are a few problems with this that I just had to just happened to catch my eye when I was reading this earlier. One is it's actually failing motion. So see this one, and motion is yeah, it's not proper. You see like the red thing moving in the background, which we don't expect. So oh yes, the reflections are not consistent as well. So yeah, there are like a few problems with this. But overall results seem decent enough. I guess. Um, I guess like there's also this one which has like uh, things moving on the extreme left with which the user did not specify. So yeah, there's I guess like some of these problems, but it still seems to work well, or at least like decent enough. Um, yeah, there was one more thing. So yeah, I guess like if you so these are like these where you give it some trajectory and it like has to follow that trajectory. So um I think like there's a few problems with this. If you particularly see like a few frames, those have like really different looking things. I don't know if you see like the white things on this big screen, but there seems to be like in the last frame or the first frame, whatever it is, there seems to be like a lot of noise in that one frame. So uh doesn't seem like fully solved yet. But yeah.
I think that's because the first image, like the input image itself, has those white spots.
No. Oh, so in that case, like you would expect all the images to have it, right? I guess. So, uh, yeah, but there seem to be like a few problems. And then they also have like this facial image animation results. They had like a video. Yeah, and I actually thought like this part was pretty accurate. Uh, so that's actually interesting. But yeah, all of these are, however, by the way, these are only like 14 frames. So very, very immensely short. Uh, but yeah, that is, I guess, like about the paper.
Like, yep. Right. Yeah, thanks everyone for attending. Um, we are trying to host these events like every week on Saturday, probably same time. So you can keep an eye out on our social media for whenever next week events is. And if you would like to discuss some papers yourself, or you would want some specific papers to be discussed, feel free to reach out to us on Discord. And also feel free to take home some shawarma